Picking up where we left off last time, let me go ahead and get my pen here. Let's recall what our first eigenvector looked like. Okay, so it was n superscript 1 equals 3, and it was minus 1 plus the square root of 3, right, times I, like that. And the case we had was nu1 equals 3. Okay. Now, the second eigenvector is obtained using exactly the same process that we did before. And what's neat about this is that if they are positive and negative reciprocals of one another, and by reciprocal I just mean different sign, not necessarily by fraction, then you're going to notice something about the second eigenvector. It'll be 3, okay, same value, but it will be minus 1 minus the square root of 3 times I, okay? And same exact deal, nu2 equals 3. This is the really nice thing about eigenvalues that are just the opposite signs of one another. You can easily get the second eigenvector basically for free. Of course, you could plug it in yourself and find the result exactly the same way, just to give yourself the extra confidence you need to be doubly sure that you have the right answer. But I'd like to save you guys some effort, especially doing your final, to get these results a bit more efficiently. So that's something to look out for. Just want to make sure you guys know that trick. And also, from here, we can now move forward and get a solution. All right, so the solution that we get from the first eigenvalue and eigenvector is the following. And this is based off our previous lecture. It's going to be x sub 1 of t. It's going to equal e, okay? And then we put in our eigenvalue, which is 3 times the square root of 3 times I times t, okay? And then it's going to be multiplied by our eigenvector, which is 3 minus 1 plus, I believe, yes, plus the square root of 3 times I. Okay, so that's our first one, our first solution. So, as we can see, there are complex numbers in both the exponential, you guys can see that, and the vector, the eigenvector itself, that we will need to get rid of in order to use this as an actual solution, right? So engineers can't use complex values to actually model bridges, right? As real as they are as numbers in mathematics, they simply don't exist in reality. You can't measure the imaginary numbers, right, with a ruler or anything like that. That is reserved strictly for the real numbers, okay? So how do we do that? So you're going to have to recall back from our discussion on complex roots, the section of second order differential equations where we use Euler's formula to get the complex number out of the exponential, okay? So doing this, we get the following. Using Euler's formula, we get x 1 of t, all right, is going to equal cosine, all right, 3 times the square root of 3, all right, times t, okay, plus 3, oh, mistake, there's a little mistake here. I'll erase that. Again, let me grab my pen. Plus 3i, I believe, or is it I? It's I. This is Euler's formula. I times sine of 3, okay, times the square root of 3 times t, okay, double close, and then we have our vector, which is 3 minus 1 plus the square root of 3. Again, that looks terrible. Go ahead and erase that. And let's see, square root of 3, that's better, times I, just like that. And again, let me close the parenthesis there. So I want to discuss with you how that conversion took place, right? So you'll notice that the e term goes away, and it's replaced by cosine plus I sine, right? And you'll notice that the I term as well disappears, at least initially, but it's again here and here. And what's nice about that is when you carry through this multiplication, the I term will essentially disappear. And that's the cool thing about this process. All right, so again, we just take the eigenvalue itself, which is this 3 root 3 business up here, and that gets plugged directly in to these two inputs here and here. So that's all it takes to use Euler's formula. So I just want you guys to see that connection, okay, just to make things a bit easier. All right, with that being said, the next step is then to multiply the cosines and sines into the eigenvector that we have over here on the right-hand side, okay, on the far right. And so doing that, we get a pretty interesting expansion. Let me reserve that for the next page here so you guys can see what that expansion looks like. So let's write this out carefully. This will be x vector 1 of t, okay, and then this is going to equal, and I'm going to have to give you guys some space. This is a fairly big expansion. The first element is going to be 3 times the cosine, 3 times the square root of 3, okay, times t, okay, plus, and then it's going to be 3 times I sine, and this will be 3 times the square root of 3 times t, and close. All right. And then the one below it, the second element, is a bit more complex. It's minus cosine, to make sure I use space carefully. And it's going to be 3 times the square root of 3 times t, just like that, minus I times sine, okay, of 3 times the square root of 3 times t, okay, just like this, plus the square root of 3, all right, times I times the cosine, all right, of 3 times the square root of 3 times t, all right, minus, and let's see if I can fit the square root of 3 times the sine. No, I can't. So let me just extend it just down 1. So forgive that. I just ran a little bit out of space. It's going to be minus square root of 3 times sine of 3 times the square root of 3 times t, close. And so imagine that's all one addition and subtraction, and that this represents the first element up here. This is the first element, and this right here represents the second element. Okay, so I want to make sure you guys see that, and let me just erase those so that doesn't make it even more confusing. All right, so now that we have that, the next step is to combine the terms with the I in them and split these terms off so that those terms that don't contain an I don't interfere. And we also factor out the I out of the vector. So ultimately, what we get is the following. We get x 1 of t, okay? And what this is going to equal is two sets of vectors. So I'll write the first one up here. That'll be 3 times cosine of 3 times root 3 times t, okay? And then below we have minus cosine of 3 times root 3, all right, times t, minus root 3 times sine, okay, of 3 root 3 times t, close and close. Okay, so that's the first one. And we're going to add this to the complex term by factoring out I over here. And so this gives us 3 times sine of 3 times root 3 times t. Okay. And then, let me go ahead and just unzoom here, make that nice and even. There we go. Sorry about that. Second term, sorry, let me go ahead and write that out. That's going to be minus sine 3 times root 3 times t, okay, plus root 3 cosine of 3 root 3 times t, okay, and then close, close. All right, and ultimately, this setup that I'm showing you does equal something very special. Ultimately, this is the real part, which is u1 of t, okay, plus I of v of t, okay? And we're going to take advantage of that setup here in the next video. Stay tuned.